Hi, I'm Ben-Yaakov. This presentation is entitled A Recent Extension to Thevenin's Theorem. Also, it's a solution to a previously posted riddle related to equivalent circuits. Now, the presentation was inspired and is partially based on the paper by Professor Ivo Barbie. Here's the paper published in IEEE Access. It's an open access journal, and it deals with a equivalent circuit. Actually, it's an extension to Thevenin theorem. So let me first talk about the riddle that I posted and show the answer, and then we'll go on. So the riddle went like this. There are two boxes here. In one, there is a circuit that is according to the Thevenin equivalent circuit, and in the other, according to the Norton equivalent circuit. The two boxes are sealed, you can't see what's inside. And the question was, how can you determine by external measurements which is which? Whether you have a box with the Thevenin equivalent circuit or a Norton. Now the point is that being an equivalent circuit, the electrical behavior of the terminal is the same. So you cannot distinguish between them by electrical measurements. However, the Norton equivalent circuit is dissipating power with open circuit because there is a current source which is feeding a resistor. This is 1 volt. The open circuit here is also 1 volt, but here there is a continuous dissipation of power. So therefore, by touching the box or measuring the temperature if you wish, you'll find that the temperature of this box has to be or will be higher than the temperature of this box. And by this you can tell that this is the Norton box and this is the Thevenin box. Not only that, you can check yourself by making a short at the output. Now the Norton does not dissipate any power because there is a short. The current goes into a short, there is no power, there's no voltage across the resistor. And here, however, the current is passing through the 1 ohm resistor, so it's again 1 watt, and obviously the box will get warm. So this is the answer to the riddle that I've posted earlier, which is kind of an introduction to what we are going to talk in this presentation. Now, before that, let me just point out that sometimes we overlook the fact that both the Thevenin and the Norton presentation do not tell us anything about the internal losses or power dissipation of a circuit. Suppose I have a circuit like this, a network like this, that's a DC network. These are fixed voltages, and there are some resistors. Here are the terminals. Now this circuit obviously passes current, and there is some power dissipation in here. The Thevenin and the Norton don't show it at all. It's sort of transparent to this problem. You cannot tell from the equivalent circuit how much power is dissipated in the circuit. This is a shortcoming of the Thevenin, which we've lived with for many, many years. Now, the finding of Professor Barbie in the paper that I've indicated is the following, which is kind of amazing. He found, and he shows, and he actually proved, that if you have a circuit with voltage sources inside and resistors, it's a DC circuit, then the part of the internal loss is constant, and it is independent on the loading. That is, you can load it by a resistor, a short, open circuit. This part here is constant, which is not sort of self-evident. And then, aside from this power loss, you have the regular Thevenin equivalent circuit. And of course, if you have current here, be some more losses, internal losses due to the current passing at the output. But this part, which of course you can find by open circuit and see what's the power dissipation, is constant, independent of the type of the load. So once you say that the power dissipation is constant, the internal power dissipation is constant, and you have an equivalent Thevenin voltage source, then you can represent this dissipation by a resistor which is in parallel to this voltage. This will not interfere with the terminal behavior, the behavior at the input or the output of this block, because it's in parallel to a voltage source. It is just dissipating power, and this is the power which is constant, because this is constant, the voltage source is constant for a given system. So this is the extended equivalent circuit that Professor Bavri have shown in his paper. So to build this equivalent circuit, you first extract the Thevenin equivalent circuit like regularly, open circuit, resistance, and then you find the power dissipation of your original circuit, and then you calculate the value of resistance for this Rx resistance such that the power dissipated by this resistor when connected in parallel to the Thevenin voltage source equivalent will be the one that is in the circuit, and that will be it. And then you can load it with whatever you want, and you know that this is now constant. So in order to check it, just to demonstrate it, I should say, I've just run a simulation. Now the first part here is starting with a circuit, just 3 voltage sources. This is 1 volt, the parameter is 1, so this is 3 volt, 1 volt, 1 volt, and then some resistor, just a random here. And here is the loading. This is the output terminal. This is the load, which I assume to be a current source, which is now 0. So it's an open circuit now. And from this, I can get the voltage at the open circuit, which is the source of the Thevenin. And then by injecting, which I'm not showing here, a current into here with these voltages shorted, I can get the output resistance, which is here. Now, when we have these sources, open circuit here, I can calculate how much power is delivered by these sources, which is the dissipated power. And this is just the current times the voltage. So it's the current of, say, V1 times the voltage across it, which is 3 volts. So it's a 3, and same for the other one, I'm adding up. So what I found that under these conditions, the internal dissipation is 1.8 watts for this circuit. So now I can take this 1.8 watt, and knowing the voltage of this equivalent source, I can calculate, and actually I've put here an expression, what is the value of this resistance that will dissipate this power. Okay, so this is V squared over the power. And here is a sort of a sanity check. I'm now calculating here the total power that comes out of this Thevenin source. In this case, it's only going here because there's no current here. And of course, this is now 1.87. This is the power that goes here, which is this power. Just everything is consistent. Now I run the simulation with 1 amp source, current source, as a load. Put it here and put it here. Now, because I've extracted the Thevenin parameters, then obviously the voltage here will be correct. This is 190 millivolts, this is 190 millivolts, that's fine. Also, I find now the total power coming out of these sources is 2.52, and when I look up the total power coming out of this source, it's also 2.52. And I find here that the power dissipated by this resistor is 1.87. This is exactly what was before for the open circuit. So we see that indeed we see the same power, which is not surprising because it's hooked up to the same voltage, and the voltage is not affected by the loading. However, I can do a sort of a sanity check here and say the following. The total power dissipated is 2.52. This is all these sources. The power dissipated by the equivalent Thevenin resistance is this. The output going out is this. and I end up with this value, which should be then the constant power, and indeed it is the power dissipated here and consistent with what we have. So we see that this really works very well and as anticipated. And again, this is not a proof, this is just an example to show that indeed this is the case. Now, Professor Barbie proved it by doing a circuit analysis on a general case. This is just a private, but this is a general case. And this is just one page of the derivation. There are some, more pages to it. I'm not going to go through it, and my objective here is really to explain the whole thing in a more intuitive way. Why is it that indeed in a circuit like this, when you have voltage sources here and resistors, the power loss will be independent on the load? This is what I like to explain in a more intuitive way. So to do that, let me start with a point to clarify the way I'm going to use a current source. Now I'm going to load this circuit, or the system that I'm examining, a general system, with a current load. And I'm saying here that this current source actually represents any load, although it's a current source. The reason is that if you put a resistor, say as a load, obviously you'll have some current, and then you'll have a voltage across it. So if you just at this point replace this resistor by a current source of this value, from the point of view of the system, it looks the same. This means that a current source actually represents all the cases, even a short. Because in a short, suppose you have a short, there is a current passing through. So if you put a current source with this current here, it'll cause zero voltage, which is like a short. So the current source actually represents all cases, and this is a justification for using it. So now I'm going to do the following. Here we have the general system, many sources, many resistors. I'm going to take one source, put it by itself, and short all the other. Namely, I'm going to work in superposition, okay? So I have this source, and what is left is sort of a network like this. This is this network which is left after I've taken out the source. Okay. So now I'm going to see what happens when this part here, the one that I'm now examining, has an open circuit. Well, if it has an open circuit, then obviously I have here some dissipation, because in a general case there might be some current flowing around this voltage source and dissipating power. And I can represent this dissipation by an equivalent resistor parallel to V1 for this case. Or if I'll find the Thevenin equivalent of this circuit by the regular procedure, like here I have the open voltage already, and then I can look at the input resistance, I'll see it in a minute. Then I can calculate another resistor corresponding to this value, which will dissipate the same power. So now I've taken care of the power that was dissipated when this circuit is just with one source, open circuit. Now I'm going to short this voltage and inject a current. Okay? And obviously, this circuit behaves like a regular circuit, and therefore Thevenin equivalent circuit holds. Therefore, this circuit has a certain resistance, which I can find from here. This is this resistance. The power dissipated in this resistance is this I squared injected times RT, or whatever will be the load eventually if I'll go back and return the voltage. That is, this is superposition. This is just looking the internal losses and the effect of the output current. And then I combine them again and I get everything, which turns out then that this everything includes this resistor for this source and a series resistance per Thevenin theorem. Now I can add all the other sources, because I'm working here in superposition, so I can say, okay, this is the contribution of this one, this is the contribution of this one, and this is of this one. And looking here inside, I can find a Thevenin equivalent for the voltages and the resistance, and counting and sort of bookkeeping all the losses here, I can calculate a resistor which will account for the total losses, internal losses of this resistor. So what I did, let me just go over it very briefly. I have sort of separated this circuit into individual sources by superposition, and then again by superposition looked at the power dissipated here without a load, and then looking at the effect of the load on the power and the output resistance, and I come up with this circuit which now combined all the internal voltages and the total output impedance that I can see here. Now the question is this equivalent circuit universal? Now, as Professor Barbie pointed out, he examined the case of having only independent voltage sources in the system and resistors. As it turns out, that whereas this is absolutely correct for this situation, there are other situations in which this does not hold. And here is a very, very simple example which shows that in some cases, especially when you have current sources, this constant dissipated power does not hold. For example, I have here just a system which is one current source and one internal resistance. This is just the system that I'm examining. And what I see is the following. With an open circuit, this system dissipates this power. When it is shorted, as I've shown earlier in connection with the riddle, when I short out the terminals, there's no power loss. So this actually shows that the assertion that the power loss, internal power loss, is constant, independent on the loading, is incorrect in this case. So hopefully Professor Barbie will extend the analysis to other cases, including current sources, and perhaps we'll have a more unified equivalent circuit for the cases of voltage sources, just current sources, and maybe a combination of the two. So this brings me to the end of this presentation. I hope you found it of interest, and perhaps it will be useful to you somehow in the future. Thank you very much.